Okay, there's some other things that we can do with the ideal gas model. We have a bunch of gases that we can look up the properties on in the tables and get really decent values. Following that model, we've done a whole bunch of calculations that things work. Okay, but let's look at this. Remember this. Remember. For an ideal gas, okay, that internal energy is a function of temperature. Okay, we just said that it's a function of temperature. Okay, and remember this, that C sub V, the specific heat at constant volume, is also a function of temperature. Not time temperature, it's a function of temperature. This equals du over dt. It's the change in internal energy over dt. Okay, so if we separate variables here, we can say that du is equal to C sub V T times dt. Right, so we can find this. We can, if we go through that and we integrate here, integrating between 1 and 2 and 1 and 2, we're going to get the internal energy at state 2 minus the internal energy at state 1 is going to be equal to this integral from 1 to 2 of C sub V dt. Sorry, I had to pause it. I had a phone call there. So U2 minus U1 is equal to the integral of C sub V T, the specific heat at constant temperature, the specific heat at constant volume at whatever temperature you're at, times dt. Excuse me. And so what's happening here is the table values that you're looking at in the appendices, what they do is they do this integral for you. They know how specific heat changes with temperature, and they're going to integrate this from some known internal energy to some unknown internal energy, and they're going to be going through this whole calculation and doing that calculation for you. Okay, that's where they show those are these table values. Now, there are cases, however, where you don't want to use the tables. You can say something. You can say this. Let's assume that the specific heat is constant. Okay, because it is. Specific heat is constant over a small range of temperatures. You often can say the specific heat doesn't change that much. I think we looked at that a little bit in the back of our book and can kind of understand that. So if we assume the specific heat is constant, what happens now is that C sub V can be moved outside of the integral, and you get this, that U2 minus U1 is equal to C sub V times T2 minus T1. We can calculate the change in internal energy by coming up with a constant specific heat, take it times delta T, and get a pretty good estimation of what our change in internal energy is. So, sometimes your problems are going to say, okay, I'm going to solve a problem, and I know it's not, I'm going to assume, first of all, I'm going to follow an ideal gas model. So that may go, now we may move a little bit away from our expected, our real number that a real gas calculation would give us. And so there's going to be a little bit of error, okay? Now, we could say, okay, with that little bit of error, we're going to now look all our values up in the tables and get as good of numbers as we possibly can for our calculation. Or we can say, you know what, we've already gotten a little bit of error. I now want to put in just a little bit more error and assume that the values are constant specific heats, and I can calculate my values using this equation. U2 minus U1 is equal to C sub V T2 minus T1. Really, this is a really very good equation, and it's going to get us really good numbers. But I want you to know what you're doing here. You are accepting a little bit and a little bit more error as you go through your calculations. But you know what? This calculation is much, much easier to work with. I don't have to do any interpolation when I deal with this calculation. I should point over here with this calculation. I don't have to do any interpolation. I can just look up specific heat. I can look at my temperatures. I can get my delta U, and I can be done with it. In fact, this calculation sometimes can save me 5 or 6 minutes when I'm working on a problem, okay? Now, your problem will tell you in Wiley Plus whether they want you to use a constant specific heat or a variable specific heat method, okay? constant specific heat method, they're going to give you a C sub V. Okay, they're going to give you a C sub V, or they'll give you some other information that says assume constant specific heats. Otherwise, you're going to use variable specific heats. What are variable specific heats? Here. These are the values that come from variable specific heats. All right? So just note that for ideal gases, and only for ideal gases, you can change U2 minus U1, the change in internal energy, to C sub V T2 minus T1. Now, similarly, we know that C sub P as a function of temperature is equal to dH over dt. And so if we do the same type of thing where we separate and say dH is equal to C sub P times dt, we can integrate this from 1 to 2 and integrate this from 1 to 2, and we can get that enthalpy at state 2 minus enthalpy at state 1 is equal to, from 1 to 2, of C sub P dt. And this is where the table values come from, where the book goes and knows how specific heat at constant pressure changes and integrates this and puts that calculation, puts it into your tables. However, if you want to assume a constant pressure, if you want to assume a constant specific heat, so assuming C sub P is equal to constant, what we can get here is H2 minus H1 is equal to C sub P times T2 minus T1. And the same things apply. We're still using an appreciable amount of error that we put inside of there. But we can only do this for ideal gases. We can only do this for ideal gases, and we can only do it with constant specific heats. We can only do it in those situations. Okay? Now, one last thing to talk about today here, and that is the following. We know that enthalpy is equal to internal energy plus PV. Or for ideal gas, enthalpy is equal to internal energy plus RT. Okay? Let's differentiate. This equation with respect to temperature. Okay, what are we going to get? We are going to get here that dH all over dt is equal to du over dt plus R. Okay? What is this telling us? This is really saying this is equal to C sub P is equal to C sub V plus R. So for ideal gases, we can replace, convert between C sub P and C sub V by this equation. By taking C sub V plus R, or C sub P minus R, and getting C sub V. This is what we can do. Okay? Now, let's also recall that the specific heat ratio K is equal to C sub P all over C sub V. Okay? C sub P is equal to C sub V. So if I do this, I can say, well, C sub P is going to be equal to K times C sub V. And I could also say that C sub V is equal to C sub P all over K. And I can do this, some algebra here. So we can say here, if I want to go up into this equation, and I want to replace C sub V in this equation with C sub P, I can get C sub P is equal to C sub P over K plus R. And now I'm going to do some algebra. I'm going to multiply through by K. So K times C sub P is equal to C sub P plus KR. And I can get, let's do it this way. C sub P is equal to K minus 1 is equal to KR. Or I could say that C sub P is equal to K times R all over K minus 1. This equation, which is on your equation sheet, is the way we can calculate C sub P. We can calculate it using, if they give us the specific heat ratio, we can calculate what our C sub P, or our specific heat at constant pressure, is. Okay, now let's see how we would calculate what our C sub V is. Okay, we can go up here to the same calculation that we had before, and we can say, I'm just going to go over here to the side. I can say that C sub P, we can say K times C sub v is equal to C sub v plus r. Or I can say C sub v times k minus 1 is equal to r. Or I can say that C sub v is equal to r all over k minus 1. Okay, so that's how we can calculate what C sub v is equal to. Okay, now these are good ways to calculate or to find out what the values are for C sub p and C sub v. And sometimes in some problems they will give us k. If a problem gives us k, what we know is that that's a specific heat ratio, and we're going to assume if they give us a k value that they're assuming that C sub p over C sub v is a constant ratio. If that is a constant ratio, that means that it's a constant specific heat method. So another way that the problem will tell us if we need to use constant specific heats to solve it, they'll either say directly, use constant specific heats, or they will give us a C sub p or C sub v, or they will give us a k. If they give us any of those things, we know that we can use a constant specific heat method. Now, I want to show you this thing that I talked to you about back in a couple lectures ago, table A19. You see green tower boxwoods. I'm trimming some stuff outside my house. Green tower boxwoods. Table A21, sorry. Table A21. This is the variation of C sub p for selected ideal gases. Here is another way that we can find out what the specific heat at constant pressure is for ideal gases. This is those equations I talked to you about. If you want us to program this into a computer, you would use these equations. But I'm telling you that we're not going to use this table in our study of Thermo 1. But we are going to use this footnote. This footnote is very important. Okay, it says for monatomic gases such as helium, neon, argon, C sub p is constant. C sub p bar is constant over a wide temperature range and is equal to 5/2 R bar. So, if you are given a problem and there's no tables in the back of the book to solve it, for example, you're given a problem that has helium in it, or neon in it, or argon in it, you can't use a variable specific heat method because we don't have any tables that gave you enthalpies or internal energies. We don't have them. So you have to use a constant specific heat method. And then you go look for your specific heats and you're saying, I don't know where the specific heats are for these values. What do? You go and look at the footnote of this figure, of this table, and you can say, okay, I remember now that I can use, for helium, neon, argon, I can use that C sub p is equal to 5/2 R bar. Now this doesn't tell you what C sub v is equal to, but you know how to find C sub v because C sub v is equal to C sub p minus R. Okay, or C sub p minus R bar. You can put this in molar basis and find out what C sub v is equal to as well. So this is a very valuable footnote, probably the most important footnote in the whole book. Make sure that you can use that. All right, now we'll end with this one thing. You know that delta U is equal to C sub v delta T. And you know that delta H is equal to C sub p times delta T. These you can use for ideal gases when you have constant specific heats. Okay? Remember this, what I said to you when we talk about specific heat. All you do here is you replace delta U with C sub v delta T. You do not have to say, well, this was a variable volume problem, I can't use this. No. You don't say for delta H, I can only use this delta H if it's a constant pressure problem. No. What's happening here is you can use this whenever it's an ideal gas, whenever it says constant specific heats. No matter if the pressure is constant or the volume is constant or the volume is variable or the pressure is variable, I don't care. You can use this equation anytime. Okay? Now sometimes students forget, what do I use? Do I use C sub v for delta U or C sub p? For me, it's a very easy way to remember. In this I remember T, delta U, C sub v. T, delta U, C sub p. 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 T, del U, V. T, U, V. Alphabetically, T, U, V. That helps me remember always for internal energy, use C sub V. Now for enthalpy, I remember that Harry Potter likes T. Harry Potter, the boy magician. If you haven't read the Harry Potter books, I don't know what to tell you. Almost everybody has. But Harry Potter, he's English. English people like their tea in the afternoon. I'm just assuming. I'm watching a lot of English shows and they like tea, and I never drank tea very much. I like some chai tea every once in a while, but I've never really got into tea. But they want a tea and they want a cookie. A cookie sounds good, or a biscuit. I'm just learning all this stuff about Great Britain, and they're just very, very proper. There's very proper tea time that they have there. Anyway, it doesn't really matter. This is thermodynamics. Harry Potter likes tea and thermodynamics. We'll go with it that way. That's how we'll remember these two things. Okay, now what I've given to you in this lecture and lecture today, I've opened up problems, so many problems that you can do. I mean, thousands and thousands and thousands of problems to do, and I can't literally do every one of those problems. But I'm going to start the next lecture in trying to teach you how we think about going about solving these problems, how we go through our thought process of ignoring all of the static, and how do we get the real information that we need to solve problems. Because what you can feel like right now is that you're drinking out of a fire hose and there's just so much information coming at you. And it is. So we're going to do a flow chart to start off next lecture to try to systematically walk you through a problem so that you can feel comfortable in what you're doing. And this just takes practice, and it takes practice, and it takes practice. So please, when you're doing your homework, try to do it the right way. Use your equation sheet. Try to figure out what are your knowns and your unknowns. Make your assumptions. Draw your diagrams. Try to get yourself in the right place, because right now we're going to deal with, it's kind of a choose your own adventure game. And your adventure can be very, very exciting if you don't do the right thing. Okay, we'll end it there, and I'll see you tomorrow.